Today's lesson is going to focus on the mole. This is one of the most important units of measurement in chemistry. The term the mole makes a lot of us think of a type of rodent, but that is not the way it is used in chemistry. Mole is short form for molecule, and we use the term of the molecule as an actual unit of measurement for counting particles. So it is an SI unit, which means System International. This means that it is a internationally recognized unit of measurement for chemistry. And 1 mole represents 6.02 times 10 to the 23 objects. Now in chemistry, we're not really talking about objects like, desks and chairs or pencils. We're talking about objects such as particles, but more specifically, atoms and molecules. Okay, so related to elements and compounds. So the number is also called Avogadro's number, named after the man who discovered it. So the man who discovered it, his name was Amedeo Avogadro. He was an Italian scientist. And he came up with this constant value to represent numbers of particles in chemistry. It is a very famous unit. Okay, so most chemistry people have a real fondness for the mole unit. And you can see here, there's all kinds of little cartoons using an actual rodent mole with the value. And we also have National Mole Day. So National Mole Day happens on October 23rd. And the reason for that is that it is the 10th month, which is October 23rd day. And it's usually very specific. It starts at 6:02 in the morning and ends at 6:02 at night. So why do we use the unit of the mole? Such a huge number. In what possible way could we use it? Well, we have to use it because atoms are so small, we cannot see them with our own eyes, and currently we cannot see them with any kind of device or lab equipment. So we use the mole to help us count atoms, if we're talking about an element, or molecules, if we're talking about a compound. For compounds, especially ionics, we may also use a term called a formula unit. Okay, so a formula unit will refer specifically to ionic compounds. Molecules will refer specifically to covalent compounds. And the conversion is, just the constant value, that 1 mole equals Avogadro's number, which equals 6.02 times 10 to the 23. And there is a unit on there. Again, it's either atoms or molecules, depending on the type of substance that you're talking about. The formula that we use to convert between atoms and molecules and the mole value or the mole constant is this formula right here. So little n equals capital N divided by NA. And I did not come up with this formula or the symbols. They've chosen all, letter N's for here, but lowercase n represents the mole. And the unit for the mole is mole with no E. Okay, so they use MOL as the unit for it. NA refers to Avogadro's number, which is this constant, should be Avogadro's number, which is this constant value of 6.02 times 10 to the 23. And again, the unit on that depends on whether you're talking about an element or a compound. And capital N refers to the actual number of atoms or molecules. Okay, so lots of times we won't have 6.02 times 10 to the 23 of something. We will have, maybe twice that amount, maybe, 3/4 that amount. And so what we can figure out is the actual number of atoms or molecules if we don't have 1 mole. If we have more or less, we have an ability to figure out the exact amount. It is a really large number, the mole, really, really big. But it makes sense because these atoms are so small. So if you just even have a speck of dust, you have this many molecules or atoms collecting to create enough mass for our eyes to see. So let's go through and practice doing some calculations when we don't have exactly 1 mole. So we know that 1 mole equals 6.02 times 10 to the 23 particles. But here's a question where it says, you know, we have 2.5 moles. So how many atoms are present in a sample of iron? So notice that iron is an element, and because it's an element, it's the simplest type of matter, we're going to deal in a unit of atoms. So we know our base formula is such: lowercase n equals capital N over Na. I want to solve for capital N. This is the actual number of atoms or molecules. And in order to do that, I have to get rid of Na, so the constant that is in the denominator, and I'm just going to cross multiply it to the other side. We always say, us non-math teachers, that if you're dividing Na over here, when you bring it to the other side, you're going to do the opposite mathematical calculation, which would be multiplying it. So we're going to tell everybody what we're solving for in brackets, okay? And then we're going to take lowercase n times Na. So the mole value is 2.5 mole. So remember, the unit is just MOL with no E. And we're going to multiply that by Na, which is Avogadro's number. So 6.02 times 10 to the 23. Now, what is the unit that we use for Avogadro's number? Well, it is the value of the number of objects or particles per mole. And in this case, because we're talking about an element, the unit is atoms per mole. We calculate this. So we have 2.5 times 6.02 exp 23. And the calculator gives me 4 significant figures. I am going to round to 2 significant figures because this is my rules, and I'm going to round to the data that is given. Okay, this right here, this is a constant. And so with constants that are given, we never include them in rounding of significant figures because they are not measured data. They are constants. So my measured data is this, 2.5 moles. I need 2 sig figs in my final answer, which is 1.5 times 10 to the 24 atoms. In the next question, we have how many moles are in a sample of 6.0 times 10 to the 24 molecules of water. So this is the actual number of molecules, which is capital N. And they're asking us for the number of moles. So you're going to notice that they never give you Avogadro's number in these questions. They assume that you know this. So we want to figure out moles, which is lowercase n, and we're going to state what we're solving for, so moles of water. And we're going to use our base formula, so capital N, which is molecules divided by Avogadro's number. Now we're using the unit of molecules because we're talking about water, and water is a compound. So we have to switch the unit from atoms to molecules. So 6.0 times 10 to the 24 molecules, and we're going to divide by Avogadro's number, which is 6.02 times 10 to the 23. And then this unit is, again, a per mole unit, but it's going to be molecules per mole, because I am dealing with a compound. So we punch this into our calculator. So we're going to hit 6.0 exp 24, and then we divide by our constant 6.02 exp 23, and I get a value of 9.966777. I need 2 sig figs. I'm going to round that to 10 moles, and I have to put a decimal after to ensure that I have a 2 significant figure value that is rounded. Let's do a couple more examples that will just sort of elaborate on our base formula. So it says, how many molecules are present in a sample of 5 moles of carbon dioxide? So again, we're dealing with a compound. This is why my unit is going to be in molecules. Molecules, the symbol is capital N. Okay, capital N is actual atoms or molecules of your substance. And we know that the base formula is lowercase n equals atoms or molecules divided by Avogadro. Avogadro's number. I need to solve for molecules of CO2. So I'm just going to rearrange my formula. I'm going to take my denominator and I'm going to cross multiply it by my mole value. So I know that I have more than 1 mole. I have 5.0, which is my measured data, 2 sig figs. I'm going to multiply that by the constant, Avogadro's number, 6.02 times 10 to the 23. We're talking about a compound, so my unit will be molecules per mole. And then I'm going to come up with an answer of 5 times 6.02 exp 23. And I'm going to get a value of 3.0 times 10 to the 24 molecules. Okay. Now in B, it says how many atoms in total are present in this sample. So this is asking us now about atoms, and we're still talking about a compound. And what we know is that when we look at a formula unit of carbon dioxide, so here it is right here, we know the formula for it. When I look at carbon dioxide, I see that I have 1 atom of carbon and 2 atoms of oxygen. And here I have a total of 3 atoms per molecule for this particular substance, okay? And that changes all the time. It all depends on your chemical formula and how many atoms are in there. So this is asking us how many atoms in total are present in the sample. So because they're asking for total atoms, I'm going to count up all of the atoms and I'm going to apply it to my answer in A. If it was just asking about oxygen, I would just deal with 2 atoms in this particular example. For carbon, there's only 1 atom in a molecule. So there's no real formula here, but if we want to set it up, we're going to do number of atoms, and we have to use the number of molecules that exist. So we know that there's 3.0 times 10 to the 24 molecules in this sample, and then I'm going to multiply by 3 atoms per molecule. And this allows my molecule unit to cancel out. And then when I multiply that through, I end up with 9.0 times 10 to the 24 atoms. And when we're rounding to sig figs, again, we're not going to round here to this 3 value, which would be 1 significant figure, because this is a constant. Okay, so we never round to constant values. We round to the measured data. Here's our last example. So it says how many moles of sodium oxalate are present in a sample that contains 3.87 times 10 to the 23 atoms of sodium. So this example is maybe the trickiest of them all. We're being asked for the moles of sodium oxalate. Okay, so what we want to be figuring out is the formula for sodium oxalate. And you guys will know that you'll look at the periodic table and you'll come up with a formula of this. Okay, Na2C2O4 is our formula for sodium oxalate. So what this tells us is that in every molecule, I have 2 atoms of sodium per molecule. So 2 atoms of sodium per molecule. And what I know is that I have this huge number of atoms of sodium. And from there, I can figure out the number of molecules that I have. So I'm going to have to do a couple of steps here. So number 1, I want to figure out the molecules of sodium oxalate, because this question is asking me to figure out the moles of sodium oxalate, not just sodium. I know that I have 3.87 times 10 to the 23 atoms of sodium. And to cancel out those atoms of sodium, I have to divide out by my constant, that in the formula, I have 2 atoms of sodium per molecule. And when I set it up this way, my atoms of sodium cancel out. This is basically the opposite of what I just did in B from above. So we're going to punch that into our calculator, and we're going to figure out how many molecules do I have. And based on this, I have 1.935 times 10 to the 23 molecules of the compound. And don't round your answer here, okay? We have to do this in 2 steps. We always save as many decimals as possible, and then we round in the very final answer. This is still asking us to solve for the moles of sodium oxalate. So we're going to set up our formula, which is N divided by Na. And now we're going to sub in the values that we calculated. So 1.935 times 10 to the 23 molecules. And then I'm dividing that by Avogadro's number. So 6.02 times 10 to the 23 molecules per mole. And I get an answer of, let's calculate it here, of 0.3214, all kinds of decimals in there. I need to round this to the proper number of significant figures. All I've done is either multiplied or divided in this particular question. And the data that they gave me was 3 sig figs. So I'm going to round this to 0. This is a leading 0, 321 mole.